Hello everyone, welcome to my second video on partial fractions. So whenever you're solving partial fraction problems, you have to first look at the degree of the numerator versus the degree of the denominator. If the degree of the numerator exceeds or is equal to the degree of the denominator, the highest exponent, then we have to apply a long division. If the degree of the denominator is larger than the degree of the numerator, then in that case it breaks up into 4 subcategories. So we saw subcategory 1 and 2, so we saw distinct roots and we saw repeated roots. That was case 2. Now we're going to take a look at case 3. So we're still under the subcategory of the denominator, the degree of the denominator being larger than the degree of the numerator. So for case 3 we have irreducible roots or irreducible denominators. What do we mean by irreducible? So if we have some quadratic function ax squared plus bx plus c, then this thing here is irreducible. We cannot factor it if b squared minus 4ac is less than 0, is negative. So if you look at the linear term, the coefficient of the linear term, the b, you square it and subtract it by 4 times a times c, and you get a negative value. That means you cannot factor that term. It's irreducible. So we have to use the following case. So how do we break it up? So to look at the partial fraction decomposition, to break up the integral when it falls under case 3, what we do is, when we notice that it's an irreducible denominator, we are going to split it up in this manner, where the integral is the irreducible denominator on the bottom, and on the top, instead of having a, what we get is this extra term. We get this ax plus b on the first denominator. And then after, the next term is going to be cx plus d. So you get this, instead of just getting a constant like we saw in the first two cases, you get this cx plus d. You get a term with an x and a term which is a constant on the numerator. Okay, and all the way till the end. So depending on how many irreducible denominators we have. So if we look at this example here, you have to integrate x squared plus 2x minus 1 over x squared plus 1 times x squared plus 2 dx. How do we know this is a case 3? So first of all, I'm looking at the highest exponent. At this moment here, it may look to you like the highest exponent at the top and the highest exponent of the denominator are equal, but it's not the case, because on the bottom we have a multiplication. So if you were to multiply x squared times x squared, the highest exponent or the degree of the denominator is actually 4, because x squared times x squared is x to the 4, so the highest exponent is 4. That's bigger than the highest exponent on the numerator, therefore we don't have to apply a long division. So how do we know this is case 3 irreducible? Well, the x squared plus 1, if we focus on this bracket first, notice we could think of this as x squared or 1x squared plus 0x plus 1. This means that the a is 1, the b is 0, and the c is equal to 1. If we use this rule, b squared minus 4ac, that's equal to b squared, which is 0 squared, minus 4 times a times c, 4 times 1 times 1. Notice we get negative 4. This is a negative value. Since we got a negative value here, that means that this term here is irreducible. So don't get confused with x plus 1 squared. Notice the difference. X plus 1 squared, all that squared in brackets, is a repeated case, because it's x plus 1, all that squared. So x plus 1 times x plus 1. This would be a case 2. X squared plus 1, we have a second degree polynomial here, is irreducible because b squared minus 4c gave us a negative value. Okay, so make sure you catch the difference between the two. And same reasoning with the x squared plus 2, that's also irreducible. So typically when you have x squared plus a number, that's an irreducible case. Okay, so how do we break this up? What is the partial fraction decomposition of this integral here? Well, what we do, once we identify the fact that it's a case 3 irreducible case, we are going to write it as the integral, the first irreducible value is the x squared plus 1, which we put on the bottom. And on top, we're not going to write a, we write ax plus b. So we have two values to go find, okay, whenever you have irreducible. Plus, since we have a second case here, x squared plus 2, we have our x squared plus 2. And on top, again, cx plus d. We have two terms to go find. A term that has an x and a term that's just a value, dx. And this is how you would break it up for a case 3 irreducible denominator. Okay, so this is the partial fraction decomposition. Now let's take a look at an example and actually see how to find these values here. So in our first example over here, we have to integrate 6 divided by x squared plus 4 times x squared plus 1 dx. Okay, before we get to the example, let me just mention this is an important integral that shows up often. So the integral of dx over x squared plus a squared, this is, you can think of it as the integral of 1 over x squared plus a squared. Okay, dx, same thing. This is equal to arctan. Arctan shows up often in these problems. Okay, so we've seen already a lot of ln's show up, but arctan shows up with irreducible. So make sure you're comfortable with this. Have this one written down, and it's gonna show up. Okay, so whenever you have 1 over x squared plus another number squared, it's an arctan. Okay, and plus c. Inside the bracket of the arctan, it's x divided by a. And then in the front of it, there's the constant 1 over a, depending on the number that's over here, okay? Because we know that the derivative of arctan from calculus 1 is 1 over 1 plus x squared, okay? So the antiderivative, it's almost the same thing, and just in this case, we have an a. The a pulls out in front, okay? So keep this in mind, write it down, and it's going to show up. So with that being said, let's go ahead and look at the first example. First of all, we have to figure out why it's irreducible. Why are we under case 3? So we have x squared plus 4. Again, if we use b squared minus 4ac, there's no b term. The linear term is not there. So that's 0 minus 4ac. So these are all positive values. Since you're subtracting positive values, it becomes negative. So all these two terms give us negative values, as we saw earlier. So the partial fraction decomposition looks like this. So it's going to be not a, but ax plus b over the first term, x squared plus 4, plus the second term, again, x squared plus 1. This is irreducible. So it's going to be cx plus d over x squared plus 1 dx. Okay, so this we don't know how to integrate. By separating into parts, now we're able to do it. Let's go ahead and see how. So we ignore the integral sign and set the integrands equal to each other. So we get 6 x squared plus 4 x squared plus 1, and that's equal to ax plus b over x squared plus 4 plus cx plus d over x squared plus 1. Now the game plan is to multiply both sides by the denominator over here, leaving us with 6 on the left hand side. And if I multiply this by the whole thing up here, the x squared plus 4 would cancel with the x squared plus 4, leaving us with ax plus b times x squared plus 1. And here, if we multiply the x squared plus 4 times the x squared plus 1, on the second term, the x squared plus 1 would cancel, leaving us with cx plus d times the x squared plus 4. So here, choosing values using method 1 and choosing x values to cancel is a bit difficult, but you could probably do it that way. I'm going to go ahead and distribute and use method 2, but really it's up to you. So you might be able to get it with method 1. I'm seeing method 2 right now. Okay, so method 2, we distribute. So we get ax cubed plus ax plus bx squared plus b. Here we get plus cx cubed plus 4cx plus dx squared plus 4d. Okay, and we create an equation with the x cubed, x squared, x, and the constant. So here we have 4 equations to create. So let's write that down. X to the 3, x squared, x, and constant. Okay, so if we look at the x cubed on the left hand side, we can think of this as 0x cubed plus 0x squared plus 0x plus 6. So we have a 0 on the left side for the x cubes, and that's equal to the x cubes. We have this term here and this term here, right? So it's just a plus c. Okay, so that's for the x cubes, and sometimes I like to cancel it out when there's a lot of terms. So the x cubes are done. Now we're doing the x squareds. On the left hand side we have 0. and that's equal to, on the right hand side, we have a bx squared. So a b, I take just the constant in front, the coefficient in front. The b's done. Where else is there an x squared? We have a d here. So b plus d. Okay. Now looking at the linear term, the x, there's nothing with an x here, so on the left hand side it's 0. And then we have an a here. Let's cancel this one. Where else do we have an x? Here, 4cx. So that's 4c plus 4c, and that's it. Nothing else has an x. So this is the equation, 0 equals a plus 4c. And then lastly, the constants, we have 6 on the left hand side. And on the right hand side, we have a b plus 4d. Okay. So in order to solve this, what we have to do is use the first equation and the third, and then use the second and the fourth. Why? Because there's two equations, two unknowns. We know how to solve these. Notice the first has a and c, the third has a and 4c, so we could solve that. So let me use the first and the third. From the first equation, I'm going to move over to c, giving me a equals negative c. Now that I know the value of a is equal to the same as c, just negative, I'm going to plug that into the third equation. So here I have 0 equals, instead of a, I'm going to substitute it with negative c. So I'm substituting my a here with negative c plus 4c. And this gives me 0 equals 3c. And solving for c by dividing by 3 on both sides, we get c equals 0. Since a is negative c, negative 0 is just still 0. So a is also 0. So this canceled out two of our variables, which is great. Now let's go ahead and find b and d. We know b is equal to negative d by bringing the d over. I'm using equation 2 now. So if b is equal to negative d, I'm going to substitute it into this equation, giving us 6 equals, b is being replaced with negative d, so negative d plus 4d. Negative d plus 4d is 3d, so we get 6 equals 3d. Dividing by 3 on both sides, we get 2 equals d. Since 2 is equal to d, we know b is negative d, so that means b equals negative 2. So a canceled, c cancels, d and b are 2, one's positive, one's negative. Now that we solved for the variables, the constants here, we could plug in our information. Let's go ahead and do that. So our partial fraction decomposition becomes the integral. A is 0, that's gone. The term with the x is gone, leaving us with b. So we get negative 2 over x squared plus 4, plus the c is 0, that's gone, and the d is 2, giving us 2 over x squared plus 1 dx. Okay. And now we could go ahead and integrate these two terms. So all this is gone. This is all side work. And what we get is basically what we have up here. So we could think of this as 2, I'm going to take the 2 out, sorry, the negative 2 out, leaving me with 1 over x squared plus, we could think of it as, instead of 4, as 2 squared dx, plus the 2 here, I'm going to pull it out of the integral, and we're left with 1 over x squared plus 1 dx. So treating here 1 as a, we use our formula up here. 1 over x squared plus 1 is just arctan. So on the left hand side we have negative 2. This we said was arctan, but in this case our a is 2. So using the formula here, it's going to be 1 over a, so 1 over 2. And the integral of 1 over x squared plus a number squared, 1 over x squared plus a number squared, is 1 over that number, so 1 over 2, times tan or arctan of x divided by that number. So x divided by 2. Okay. Plus here we have 2, and then we have 1 over x squared plus 1. The a's are being replaced with 1, giving us just arctan. You can do 1 over 1, then arctan of x divided by 1, but doesn't change. And this is the answer. Negative 2 times 2 is negative 1. So it's negative arctan of x over 2 plus 2 arctan of x plus c. And this is the final answer. We are done. Okay. So that was the first example. So often with irreducible, this integral is the one we're going to use. We're going to get arctan. So a lot of arctan, ln, and and use substitutions. Those are common in partial fraction problems. So let's go ahead and take a look at the next example. So next we have case 4, which is essentially a combination of everything we've seen. So there's nothing new. We're combining case 1, 2, and 3. So we're dealing with distinct, repeated, and irreducible roots or denominators. Okay, so we're combining our knowledge on all 3 of the cases. So let's take a look at this example. Example 2, it says to evaluate the integral of x squared minus 2x minus 1 divided by x minus 1 squared, all that squared, times x squared plus 1. So pause the video, give this a shot, see if you're able to solve it. So the first thing we have to do is figure out the decomposition. How are we going to break this up? Actually, the first thing we should always check is to ensure that the denominator has a higher root, a higher exponent than the numerator. So the degree of the numerator is 2. The degree of the denominator is x minus 1 squared would give us an x squared times an x squared is x to the 4. Okay, so as long as the degree of the denominator is bigger. But if you have to see it, expand it. Like, take the time to write it out. X minus 1 times x minus 1. This gives us x squared minus 2x plus 1 times x squared plus 1. You're just distributing. And when you distribute the first 2 terms, you get an x squared times x squared, which is x to the 4. Okay, so right there we see it. The highest exponent is a 4. So the degree of the denominator is in fact bigger than the numerator, and that's good. We don't have to apply a long division. So that's always one of the first things you should check. So how do we write the partial fraction decomposition? So we're going to split this up as the integral of the numerator depends on the denominator. So on the denominator, notice we have an x minus 1 squared. This is repeated because it's squared. So the first one's going to be x minus 1 with just an a on top because that's the rule for repeated roots. Plus we go b over x minus 1 squared. Okay. So since it's repeated, it's just a constant on top. And lastly, we have the x squared plus 1, which we just saw. This is a irreducible case. We have x squared plus 1, and don't get confused with x squared minus 1. I just want to point this out. X squared minus 1 is difference of squares. You can use difference of squares to write this as x minus 1 times x plus 1. Okay, so this breaks up. So x squared minus 1 is difference of squares, which breaks up into distinct case. Okay, so we have 2 distinct roots. X squared plus 1, on the other hand, cannot be broken up. So this is irreducible. If you do b squared minus 4ac, you'll get a negative value, which means it's you cannot factor this term. Therefore, it's really important to understand the cases and to be comfortable with your factoring techniques. So therefore, x squared plus 1 breaks up into cx plus d. We get our 2 terms on the top, and that's what's important here to catch. Okay. So now what we do is we let the integrals equal each other. So this is work that we do on the side to figure out what a, b, c, and d are going to be. So on the left-hand side of the equation, we have x squared minus 2x minus 1. And I'm going to take the denominator and multiply it to each term right away. So I'll do this in one step. So if we multiply a over x minus 1 by the denominator, it gives us a times one of the x minus 1s are going to cancel, leaving us with an x minus 1 times x squared plus 1. If I do the same thing, I multiply the denominator on the b term, the x minus 1 squareds cancel, leaving me with b times x squared plus 1. And the cx plus d, the x squared plus 1 is going to cancel, leaving me with x minus 1 squared. So plus cx plus d times x minus 1 squared. Okay, so now we have to go ahead and solve this. So one way that I'm seeing to do this right now is I want to cancel out my a, c, and d. I could cancel all these terms out by substituting x with 1. If I let x equals 1, and I mentioned there's 2 methods. There's method 1, method 2. Method 1 is replacing x with a value. Method 2 is expanding. You could actually do a combination of both if that works out. So I could start off with method 1, figure out one of the variables, and then if I get stuck, I could just switch to method 2. But the answer that I found, let's say I solve for a and a is 2, I could use that afterwards in method 2. Okay, so you could actually combine both methods. But in this case here, I'm using method 1. I'm replacing my x with 1. So we get 1 squared minus 2 times 1 minus 1. That gives me minus 2. The x minus 1 here gives me 0. This whole term is cancelled. x minus 1 squared, this whole term cancels. It leaves me with just b times 1 squared plus 1, which is 2. So dividing both sides by 2, we get b equals -1. So we found one of the terms, we got our b. How can we cancel out the rest? If we let x equals 0, that cancels out the c, but it doesn't cancel out this. We'll still get 2 unknowns. So I'm not seeing how to continue with method 1, but we know b is equal to -1. So let me put that on the side. And let me go ahead and use method 2 now. So method 2 involves us to expand. Because I'm not seeing any variables I could substitute, because no matter what I replace my x with here, it's being squared and added to 1. So I can't choose an x value to cancel out this term. So I'm kind of stuck. So let me distribute. So here we get x cubed plus x minus x squared minus 1. And then all those terms multiplied by the a. So I'm going to distribute the a. So it gives me ax cubed minus ax squared plus ax minus a. So this is done. B we solved for is -1. So I'm just going to substitute this with -1. So -1 times x squared minus x squared, and -1 times 1 is -1. And here I'm going to distribute, giving me x minus 1 squared is x squared minus 2x plus 1, and that times cx plus d gives me cx cubed plus dx squared minus 2cx squared minus 2dx plus cx plus d. Okay, so distributing this, we get all these terms. So let me write it here, plus cx cubed plus dx squared minus 2cx squared minus 2dx. So very computational. You just have to keep track of your variables. Okay. And now we're going to create our equations with each term. The highest term we have is x cubed, so we're going to do one with constants, one's with constants, x squared, and x cubed. Okay, so let me do it with x cubed first. On the left hand side there's no x cubed, so we have 0 equals a that has an x cubed plus c. Okay, so that's my x cubed case, so let me just write that on the side. 0 equals a plus c. I'm just going to move that to give myself some room. Let's do the x squared. On the x squared, on the left hand side we have a 1x squared, because the coefficient of the x squared here is 1. So we get 1 equals, on the right hand side we have a negative a, that's x squared. We have a minus x, so a minus 1, that's x squared. D, so plus d, that's gone. And we have a minus 2c, that's x squared, that's gone. Okay, so here we still have 3 unknowns, so we're stuck. Let's hold off on that. Let's go look at x. For the x's we have, this is gone. For the x's we have -2 on the left hand side. This is gone. We have an a. We have, sorry, cx was cancelled. We have a minus 2d. And we have a plus c. So we still have 3 equations, 3 unknowns, so we're still stuck. So the c is done. And then for the constant, on the left hand side we have -1. And on the right hand side we have equals -a. We have a -1. And we have a d, plus d. Okay. So if we look at the last one, well, the first one, a is equal to -c. From equation 1, bringing the c over, we get -c. And from the last one here, if we bring the -1 over, the -1s, we add it over, it's 0. So we get, bringing the -a over, it becomes positive a. So we have a equals d. Okay, so a is equal to d and a is equal to -c. Which means that I could rewrite c as -a and I could substitute these two into the second and third equation to find the missing variable. So I could solve for a by substituting my c with negative a in this equation and substituting my d with a, right? So if I focus on equation 3, so I'm just going to squeeze it in here, the left hand side is negative 2. That's equal to a, I'm going to leave it. I'm going to express the equation solely in terms of a. D I'm going to replace with a, because d is equal to a from this equation. So we get negative 2a. And c we know is equal to negative a minus a. This means that a is equal to negative 2. 1 minus 2 is negative 1 minus 2a. Or you can think of it as the a's cancel. And then you divide by negative 2, so 1 equals a. Okay. Since 1 is equal to a, we have our a. That means c is equal to negative 1. It's opposite. And d is also equal to 1, because it's equal to a. So we found all the coefficients. We remember b was negative 1, a is 1, c is negative 1, d is 1. And we found the values. So let's go ahead and replace them into our integral. Okay. So the first piece, a we said was 1, so we get 1 over x minus 1, plus b we said b was negative 1, so it's a minus 1 over x minus 1 squared, plus cx plus d. C is negative 1, so negative x plus d, d is 1, and we get over x squared plus 1 dx. Okay, so we reduced it to this case, and now we could integrate each term individually. The negative x plus 1 over x squared plus 1. Whenever you have an addition or a subtraction in the numerator, you could split it up. So I always think of it as negative x over x squared plus 1 plus 1 over x squared plus 1. Okay, so we're going to split this up into two cases. So I'm going to remove this. So we have negative x over x squared plus 1. And then we have plus 1 over x squared plus 1. Okay. Now let's go ahead and see how to deal with each case individually. The first one, we know we've seen this already, so if we integrate 1 over x minus 1, using a u substitution and letting u equal x minus 1, you'll get that this is ln of x minus 1. Okay, so this one we saw, we're okay with that. This one we saw as well. Again, using a u substitution with u equals x minus 1, we'll get 1 over u squared, which when we integrate, it's u to the negative 2. Taking the integral, you get u negative 1 over negative 1. So this is going to become plus 1 over, and we know u is equal to x minus 1. Okay, so work out the details, use the u substitution, and solve it without skipping steps. But this one we've seen in an earlier video, so I'm just going to write it in shorthanded notation in terms of x. And this one over here, this one's new. So how do we integrate negative x over x squared plus 1? Well, the negative I could put it in front, it's a minus, and now we have x over x squared plus 1. How do we integrate this? Well, guess what? It's another u substitution. U substitution we use often, so make sure you're comfortable with it. Let u equal the denominator, x squared plus 1. Why? What's the derivative of u? Well, it's 2x dx. So we transform this into the x on top stays. X squared plus 1, we're going to replace it with u. So x over u. And dx, solving it for here, we'll divide both sides by 2x, is du over 2x. So I'm substituting my dx with du over 2x, and notice the x's cancel. So we're just left with a half integral of 1 over u du, which we know this is just ln, a half ln of u. But wait, what's my u? My u is x squared plus 1. Okay. So here we get minus a half. Just gonna erase this. Ln of x squared plus 1. So these first three are very common. So we had just ln, this becomes this, using a u substitution, u substitution. This one over here is also u substitution. Notice all of these have 1 degree lower on the numerator. So the degree of the denominator is 1. This is, let's say x to the 0. Here, if we focus in the bracket, the degree is 1 on the top, it's 0. And here, if we focus on the entire denominator, it's x squared, and on top we have x. If it's 1 degree less, we will get it with a u substitution. Last, we have the hardest one, 1 over x squared plus 1. We cannot use a u substitution here because we'll be left with an x on top, which won't cancel. So in this case, what do we use? What we saw earlier. Whenever it's 1 over x squared plus a number, this is arctan. Okay, so using this formula here, since it's plus 1, this was a plus. This gives us just plus arctan of x. Since it's all definite integrals, plus c. And this is the final answer. Okay. So these are the 4 most common types that we'll see. So make sure you're comfortable with all these integrals. Okay. So let's take a look at our final example. So in our example over here, it says to evaluate the integral of e to the 2x divided by e to the 2x plus 3e to the x plus 2, all that dx. So pause the video, give this a shot, see if you're able to solve. So at first glance, this does not look like what we've seen. This isn't a polynomial divided by a polynomial. So how do we solve this? So what's nice about this problem is that we could actually get it, but we just have to catch that we have to transform this, instead of using exponentials, into a polynomial. How do we do that? We have to start off with a u substitution. That's the trick to this problem. So let's begin with a u substitution. So let u equal, it works out with e to the x. Okay, let's go ahead and see why. So if we let u equal e to the x and we derive it, we get du equals e to the x du. The derivative of e to the x is e to the x. And dx, if we solve for it, divide by e to the x on both sides, we get du over e to the x. Okay. So this integral here transforms into, we could think of e to the 2x as e to the x all that squared. Okay, so we can keep it in mind, think of it this way. Divided by e to the 2x, which again we can think of as e to the x squared, plus 3 e to the x plus 2 dx. Now what we could do is transform this all in terms of u. So here, e to the x squared, we could think of it as u squared over u squared, because e to the x is u, plus 3u plus 2. And dx, we could transform it as du over e to the x. But wait, this is an issue. We have an e to the x here. This is supposed to be expressed solely in terms of u. How do we rectify this? Well, recall, e to the x is just u. So I could just write this as division by u. And this u is going to cancel with one of the u's on top. So all we're left with really is the integral of u over u squared plus 3u plus 2 du. And we reduced it to this problem here. Okay. And now this looks familiar. This is a partial fraction problem. And if we look at the exponents, the highest exponent on the numerator is a 1, the highest exponent on the denominator is a 2. So since the denominator is bigger, we don't have to apply a long division, which is great. So we have to determine what type of case are we dealing with, 1 to 4. Which case is this? Well, let's rewrite it up here. Let's write it as u squared plus 3u plus 2 du. I'm just going to keep the u substitution. And we could factor the bottom. Two numbers that multiply, it's a trinomial, so two numbers that multiply to give you 2 and add to 3. We could express this as u over u plus 2 times u plus 1. And now it's clear. This is just distinct. We're dealing with distinct roots, which means that we could separate this into the integral of some number over u plus 2 plus some number, a different number, not necessarily the same, so we'll put b over u plus 1 du. And now we apply our partial fraction. So we take this and set it equal to this without the integral. We focus on the integrand, what's inside the integral, and we set them equal to each other. So I'm going to right away write it as u, or you can think of it as x, and I'm going to multiply the denominator on the numerator here immediately, giving me a. If we multiply the first term, the a over u plus 2 times u plus 2 and u plus 1, the u plus 2's cancel, and we're left with the u plus 1 on the numerator. Same thing with the b. The u plus 1's cancel, and we're left with the u plus 2. Right? So it's essentially cross multiplication in some sense. You're taking the u plus 2 times u plus 1 and you're multiplying by that on both sides of the equation, leaving us with this. Okay. Now we use method 1 or 2, it's up to you. I'll use method 1. So let's let u equal, let's cancel out the a, so I'm going to let u equal -1. So on the left hand side of the equation we get -1 equals -1 plus 1 is 0, so this is gone, and we get b times -1 plus 2, which is just 1. This implies b equals -1, so that's done. And now let's go get our a. Canceling out the b, we're going to let u equal -2. -2 plus 2 is 0, that guy's gone. And here -2 plus 1, we get, on the left hand side it's a u, so -2, that's what we're substituting it with, equals a times -2 plus 1, which is -1. Dividing both sides by -1, we get 2 equals a. Okay, so we found the parameters a and b, or the constants a and b, and now we could substitute it into this case. So a, I'm just going to rewrite it over here. A is 2, and b we said was -1, so it's like -1. And now we know how to solve this. So this is done, giving us this. We could pull out the 2. We're left with the integral of 1 over u plus 2. Using another u substitution, we get ln of u plus 2. Just doing it the shortcut, and same thing here, we get minus ln of u plus 1, okay, plus c. And this is it. This is the answer. So it didn't look like u substitute, it didn't look like a partial fraction problem. It's hidden. With the proper u substitution, it turns into a partial fraction problem, okay? And again, still the same rules apply. You started in terms of x, you finish in terms of x. Leaving your answer like this is wrong, so be very careful. So our u is equal to e to the x, bring that back. So this is equal to 2 to the ln of e to the x plus 2 minus ln of e to the x plus 1 plus c. And this is the final answer. Note that if you would have gotten ln of e to the x, let's say there was no plus 2 or plus 1, don't leave your answer like this. Ln of e to the x is simply just x. Okay, because ln, you could think of it as log base e of e to the x. And whenever the base of the log matches the base of the exponent here, e and e are the same. The answer is just what's in the exponent. Okay, so it's x. So I hope this video helped. I hope you have a better understanding of partial fraction. This is definitely one that requires a lot of practice, so make sure you're practicing. And I'll see you in the next one.